When it comes to analytical techniques and methods, first we need to, of course, to distinguish between techniques and methods. So technique would be actually some scientific principle or classical instrumental procedure for the analysis of some group of analytes with similar physical and chemical properties. Analytical method would be more specifically specified in terms of analyzing particular analyte or particular groups of analyte, making it more selective, so you can have of course several methods by application of one analytical technique. Also, in order to distinguish also analytical methods in terms of instrumental procedures and whatever laboratory procedures from written standards, it's also important to say that written standards or some normative documents are also already prepared in many different areas, also for the analysis of such wood material, for example, or biomass materials that can be applied successfully for example, wood pellets. These type of documents are usually issued by international, regional, or national standardization institutions such as ISO, CEN, EPA, and so on. And these methods are actually done by compilation of work, of some research work in some well-known or already accredited, laboratories with already proven capacities. So in this slide you can just see some of the examples. So there are two ISO methods for the biofuels, the determination of major elements, minor elements, and also for the major elements, one EPA method. So actually these written documents is something that you can buy and apply in your laboratory, and you already have some guidance on how to validate your method, how to calibrate your instrumentation, how to test the quality of your results, and so on. The problem remains that these already existing documents are not sufficient in terms of different matrices in which you can analyze, for example, elements in solid biofuels. So they are only tested on a limited number of different matrices. It can be the case that some matrices, such as, for example, a special type of wood pellet, wood chips, or some other wooden material, and especially ash, is not covered by these standards, and you need to do some optimization steps or even validation of certain steps in the analysis in order to be able to apply these methods for these new samples. So in this very project, we are aiming for this input for standardization and to recognize what are those steps and what are those matrices that these standards can be applied to, or is there is a need to maybe develop even some new normative documents. When it comes to techniques and methods used to determine elemental composition, they usually include different types of wet chemistry processes and non-destructive methods, as we already mentioned. Metrologically speaking, optical methods or spectroscopic methods, gravimetric methods are treated as primary methods. So usually whenever you can, these type of methods should be applied, because it is much more easier to establish traceability to SI units. So in that sense, the quality of results generated by these type of techniques are usually of higher quality. But it is not always possible, and not only that, a lot of accredited laboratories, routine laboratories working in the field, are using so-called secondary methods, or methods also based on some kind of a scientific principle, but with different paths of traceability. So usually, in order for those laboratories to validate their secondary methods, they need to establish traceability toward primary methods. And it's usually the role of metrological institutes or other types of reference laboratories in any field to develop, confirm these primary methods, and to actually provide traceability to other routine laboratories, to traceability to second level. Elemental analysis usually is referring to some concentration or the amount of element present in the sample. It can be weight percent, such as it's written here. It can be volume percent, depending on the aggregate state of the sample. It can be molar percent or molar concentration, and so on. Whatever is the most suitable way of representing results for particular analysis. There are many, of course, there are many different elements and many different samples. So, and they are appearing in different concentrations. So all these three aspects needs to be taken into account when choosing the right and appropriate analytical method for the analysis. So you need to know what is the matrix, what other elements you have there that could be possibly interfering with your element, what is the form of the element, does it need some additional preparation in order to transfer it into analytical form, some form of derivatization, and of course you need to know which concentration range you want to cover. So not all analytical techniques are capable of covering large scale, talking about concentrations or a large number of different analytes. So you need to be very careful when choosing the appropriate analytical method in order to have quality results and in order to have results that can be further used for its own purpose. So I will just say something about the most prominent or the most used methods in chemical laboratory today for the elemental analysis. So, for example, atomic absorption spectroscopy is based on the detection of wavelengths of light absorbed by the element. It's usually starting from near UV part to near infrared part, covering all the visible spectra. And usually as a light source you have a hollow cathode lamp of certain elements, so you need to analyze element by element. Here you can see the scheme of such instrumentation. So you need to have your sample in a liquid form. It needs to be exposed to a certain source of heat, source of energy, where the sample will be vaporized, atomized, and where the certain elements can absorb the light from the hollow cathode lamp. On a level of absorption so the absorption itself will tell you that something about the identity of the element, so that this element that you are aiming for exists in a sample, and the intensity of absorption is actually telling you about the concentration. There are two types of these methods. So one is flame atomic absorption spectroscopy, and one is electrothermal atomic absorption spectroscopy. It's actually the source of heat is different for flame. It's flame, obviously, that can be prepared with different fuel and different oxidizer, and for electrothermal some graphite kivettes are used to heat up the sample. Electrothermal is much more suitable for trace analysis, so for very low concentration is very good technique. The only downside is actually that you need to analyze one element at a time. ICP-OES, it's one of the also optical spectroscopy methods. The principle is similar to atomic absorption. It's only that here you don't record absorption of light at certain wavelength, but you are actually recording the emission, the intensity of the emission at certain wavelength. Also, wavelength will tell you about the identity of the element, and the intensity of this emission will tell you about its concentration. A source of you also sample is in liquid form, and you also need to vaporize it, break it down, atomize it, ionize it, and so on. In this case, it's not graphite technique, it's not flame, but it's plasma actually. Plasma made from argon gas. The temperature of this plasma is approximately 10,000 kelvins, which is high enough temperature to have basically all elements that you can analyze with this technique in ionic form. That means that you will actually record the ionic spectra certain elements. Of course, each element can have different ionic spectra, so it can emit at different wavelengths, so you can choose whatever wavelength is more suitable in this particular matrix in order to evade, for example, some spectral interferences, other elements present in a sample, and so on. This is just the schematic representation of the method. You can see it's very similar to the previous one. It's only that the source of the energy is different. So you have torch here for plasma, and you are actually recording the emission instead of absorption. It's very good. So this type of instrumental analysis is actually very suitable for elemental analysis, for more than one analysis of more than one element at a time in the sample, because the detection system allows you to detect more than one different emission spectra from the torch of all the existing elements there. Atomic emission spectroscopy with microwave plasma is very, very similar to ICP-OES. It's only that the plasma is made of nitrogen instead of argon, so the plasma temperature is somewhat lower, around 6,000 degrees Celsius. So that means that depending on the energies for atomization or ionization of certain element, you can have either atomic or ionic spectra. You are also recording emission spectra, and all other principles are the same. So you need to have your sample in liquid form that can be further vaporized and atomized, and for some elements even ionized in plasma, so that emission spectra can be detected. It also allows you to determine more than one element from the same sample at a time. When it comes to ICP-MS, it's also inductively coupled plasma, also made of argon, such as for ICP-OES. It's only that the detection system is somewhat different, so it is not optical method, it is mass spectrometry. That means that you are not focused on determining the identity or the concentration by the emission spectra, but rather on the forming ions in plasma. These ions, their mass to charge ratio are fingerprint, or they are very particular for certain elements. So that is how you can use this technique. Is very powerful in terms of identification of present elements in this case, and also from the intensity of the signal you can also recover the concentration of the element. This type of instrumentation is very, very powerful. It actually gives you the opportunity to detect even PPT level. That needs to be taken with some precaution, because this detection limits generally for all these methods that we mentioned depend strongly on the matrix, sample matrix. So particularly for these techniques, and the detection system is very, very delicate, samples need to be prepared carefully, and they need to be clean from any types of possible interferences in order to allow such quantitative analysis and such low detection limits. And also the additional ability of this instrument, because the detection principle is related to mass measurement or ion mass measurement. It allows you actually also to determine the isotopic composition of certain elements, if that is of interest in particular case. X-ray fluorescence is also a very powerful technique. Sometimes it's impossible. You can see that in the all previous techniques that we mentioned, you need to somehow prepare the sample in a very rigid way. So you need to mix it with some strong oxidizing agents, acids, bases, and so on, in order to transfer it into analytical form. It needs to be a liquid, so you are completely actually destroying the sample. So that's why it's a bit harder to assess maybe the type or the form, sometimes that is also important, the form of the certain element as it is present in the sample. When you destroy the sample, you transfer all of that element in one form, so it's sometimes hard to do the speciation. For this type of analysis, you actually don't need to prepare the sample in that way. Of course, you need to do some homogenization of sample in order to get more quality result, but the sample is tested as it is. The principle is actually that you have a primary source of X-rays that is the sample that is these primary source of X-rays coming from the anode, and they are used to bombard the sample, and fluorescent or secondary X-rays are coming out of the sample, and these fluorescent X-rays are also very particular for some given element, so you can also use these X-rays, their energy or their wavelength, in order to assess the identity of the element, and by the intensity of the signal you can also assess the concentration. So as a main, this is the main principle, and all these techniques, X-ray fluorescence techniques, can be divided into two subgroups: energy dispersive or wavelength dispersive. So as I already mentioned, energy dispersive X-rays will focus on the energy of the fluorescent X-rays, so the measurements will be done in, for example, electron volts. And for the wavelengths, you will be actually focusing on the wavelengths of X-rays, and that will show you, that will tell you something about the identity of the elements. That is the fingerprint of each element. For the wavelength dispersive X-ray fluorescence, it's much more quantitative. It allows you also to filter out through the sample. You can analyze some lower concentration. You can evade spectral interferences by applying certain crystals in order to filter out all unwanted radiation. So in that sense, this type of technique is much more recommended, but it's usually these instruments are bulkier, heavier, and usually they are placed in a laboratory. In the field, usually you will find some energy dispersive XRFs, but they are somehow very related, so you can use the same types of calibration standards and so on in order to calibrate such techniques. So usually laboratories dealing with, for example, geological samples or elemental analysis in different types of samples usually dispose of both of these techniques, and they can compare the result. Here you can see the example of one of the wavelength dispersive XRF instrument. This one is equipped with a lot of different crystals, so allows you actually to analyze throughout the periodic system of elements from beryllium to uranium. You can also do some unknown sample scanning just to see what is present there, but of course for the quantitative analysis some standards are also required for the calibration. Standards also need to be in the same form as samples, and that is actually what we are trying to develop in this project. So thank you very much for the attention.